Good afternoon, everybody, and thank you really for inviting me. So, hydrology from space that you ask is such a vast domain that I decided to narrow it to my little expertise, and I will rather talk about hydrometry from space and measurements and the importance of the measurements for hydrology and, of course, its impact in the south because this is where it has a major problem. So, WMO has long reported on the losses that we have because of climate change and, of course, of the flood on the water disasters. And in top, of course, of these disasters, we have those because of drought, storms, and flood. But the very important point, if I can, is to say that most of these losses, 90% of the losses occurred in the underdeveloped countries. And as we will see, this is one of the big parts of the problem. And just as I would say a joke, I would say that I would just put that on the French government's website, you can find that the climate change costed $10 billion just in 2022. And I heard that they were looking for money, so this might be a way to find the money. So, as we just saw, so the flood, the water originated disasters are very important, are dominating on the disasters on Earth, and so you may think that this is particularly well measured, and actually it is not. And data availability is decreasing dramatically. This is a figure of the content of the measurements that we have in GRDC. I guess everybody knows what GRDC is, but just to remind, it comes from the United Nations, UNESCO, and it is supposed to collect all the measurements on the water level and discharge on Earth. And as you can see from about the end of the 90s, early 80s, the number of data available has decreased dramatically. And actually, if you have just a look on the, there is a shift on the, on the line, is that the level that we have nowadays is more or less the number of data that we had during the First World War. We are back to this. Okay, so as you can clearly see, this is far insufficient for all the scientific and societal needs. And in addition, this is not fairly distributed. Most of the data that we still have come from Europe or United Nations, and most of the lack of data comes from from Asia, Africa, and South America. And as you know, this is the places the most important in terms of water and water flows, water disasters. So, well, sorry for the shift in the figures. So, what altimetry from space could bring to this? Altimetry from space started about at the beginning of the 90s, and it has really been used for hydrology. From the 1995, so more or less the age of CEREGE here, and owing to, I would like to give a specific dedication to ESA, because Europe really was the first country or group of countries that included the measurements of water level in the satellite they launched. So, as an example of what happened, because we are talking about the underdeveloped or south countries, this figure shows the evolution of the stations, which means the evolution of the data available if you want to make a paper in the Congo Basin. So you have on the top what happened for in situ station from a study by Briquet in 93, where he could work with tens of in situ stations with more than 50 years of data, long stations, on another study that occurred that in 2021 by Mukondi in Kaya, and he just got 4 or 5 stations, just because he wanted to use in situ measurements. That's all what he found. And he was a student from Congo. It's not because there were hidden data and so on. That's the only data he got. In the meantime, if you look at the papers that were published by people using satellite data, Mélanie Becker or Adrien Paris, from 2014, 2019, they started with about 100 of stations, and now there are 500 or 600 stations. Okay, so as we will see, the sampling is not the same, also in terms of time sampling, space sampling, but of course, you can see that in the study by Adrien Paris, that you have much more information, in fact, and so you can make much more detailed studies. So, one of the questions that we had with, I would say, canal historique hydrologists, they don't like people from working with satellites. And most of the time they said, okay, your data, but they are not very accurate. We don't trust in it. So we tried a lot of studies of quality measurements, assessing the quality of the measurements. And this is a key point for the South too. They are very, very conservative, actually, and they do not trust. They really need to be convinced. I'm sorry, I think we still failed, need to be convinced of the interest of this study. So this is just one example among many others. It happened that, you see, at the beginning of the 20th century, between year 2000, 2010, we had satellites which made crossings of the Congo with 1 day apart. So if you make the very conservative assumption that the water level has not changed within 1 day, okay, which means that you include the natural variation into your budget of error, you can make a conservative estimate of the errors or the quality of the data. So these satellites, where you may know them, Envisat between 2000 2010, and Saral 2013 2016. And what you can see is that for Envisat first, 90% of the crossings had a difference less than 50 centimeters. And for Saral, so I would say the generation after, you had 90% of the crossings were below 25 centimeters. So this is not perfect, but this is quite a fair assessment of the quality of the data. And you can see on the picture that you had big rivers, of course, the Congo itself, but also you had very narrow rivers. I couldn't show everything, but you can trust me, some of them are below 100 meters, even 50 meters wide. So another point is that hydrometrists, they believe that in situ measurements, ground measurements, is some kind of biblical truth, okay? This is really truth that you must compare with. Okay, let's see. So with our colleagues from Brazil, we made a measurement in the Amazon basin. I tried to stay in the south, but to change the basin. We did the following experiment. We made absolute measurement of all the gauges in the Amazon, Solimões rivers. Okay, this is illustrated with, you see the GPS antenna on top of the gauge, and we equipped a big vessel with other GPSs. The purpose of the experiment was that every time that the ship navigates over beside the gauge, you can compute the difference between your two GPS solutions, and if everything is correct, taking into account the change of water level read on the gauge, of course, if everything is correct, you should have all your red points on the zero axis. Okay, you compute properly the difference. Okay, if there is no error in the reading of the water level, okay, you can say that the error in the GPS is a couple of centimeters. If you make, so if there is no error in the reading along the water level for each gauge, all your points should be on the zero axis. As you can see, you have difference that can reach 1 meter. okay? And the key point of this is that, okay, you have some wrong measurements. Everyone has wrong measurements. The point is that you don't know how many of them, because, of course, you had one measure of this every time the ship was navigating in between, which maybe every 3 months, every 4 months, every 5 months. But in between one measurement where you have, for example, 50 centimeter, you can see 50 centimeter error. Next time, you have 40 or you have 0. What about the measurements in between? You don't know. So the only point you know is that you can trust me, this is very general in all the, I would say, South countries. And this is error. I don't talk about the cheated data. Okay, let's be fair. All what you know is that you have a significant but unknown amount of the ground measurements which are potentially erroneous by several tens of centimeters. Okay? Just for you to keep in mind, when you want to compare some data with the others, you have to do it fairly. And the problem that we have with all the ground measurements is that up to the advent of satellite altimetry, you had no way to compare, to assess for its quality. So, what happens with satellite altimetry is that we had a big revolution in 2016. And this was mostly a technical revolution. Up to 2016, it was really taking the measurements from the oceanography satellites, pick up the data over the continents, and try to use them for hydrology. But from 2016, the technological revolution included use a SAR mode. I will very, very briefly tell you what about. Uploading onboard DIMMs, and the commitment for continuity given by ESA. And this so included all the so-called Sentinel satellites and the Copernicus program. So very briefly, what is the point with the SAR measurements? Up to 2016, the satellite emitted at what we call low rate emission in order that you can accumulate independent measurements to have a good mean, because these are independent, so when you sum them, you sum independent measurements. And this was the deal for oceanography. We want mean values for large areas. At the opposite, for hydrology, we want measurements for narrow objects. A river is just a few 100 meters when they wanted kilometer-size measurements for the ocean. So the SAR mode enables to slice, and because you emit very, very fast, and using the Doppler effect in the front and the back of your footprints, you can slice your measurements and have measurements of very narrow bounds, which is much more adapted for hydrology, of course. So, just again to show you an example of the increase in qualities that we had, we made an experiment with the CICOS. CICOS is a basin organization for the Congo Basin. Again, the purpose was to convince them that it could be very useful. So we made this experiment on this river, the Lobai River, and so the dots are the reading on the gauge, and the red points are the satellite, okay, the satellite measurements, and so the RMS error between both series is at 11 centimeters. So you see, we really made a quality improvement in the time series, and actually, if you can take into account the slight slope of the river and the fact that the measurements are not all exactly at the same measurement, you go below 10 centimeter RMS. So the second point is the onboard DEM, which means that what you do is you upload on the satellite, you upload an a priori value of your river position and height, more or less 10 meters, which is far enough for most of the rivers. And this is an example of the Sentinel satellites 3A and 3B, which means that you have about 90,000 targets that you can upload with predefined sites, targets, and you see that in this way you have you can prepare your measurements in all the southern countries. So just again to give you an example, so I will not use a Sentinel satellite. I will use a time series from the SWOT satellite that has been launched 2 years ago. And the SWOT is really a new revolution because SWOT will perform 100% coverage of the whole Earth because of these swaths. It's not only along track measurements, but swaths of measurements. And because of this, so we have much more measurements. And so on this figure, you have, you see, during the first phase of SWOT, it was on a one-day cycle, which means that on a very few places, it was coming back every day in order that we could have more measurements to validate the system. So, and at the very beginning of this phase, we had the warm-up phase, where we're just trying to turn all the buttons and to start the measurements. And you see, and it was, so we had the gauge, and you see that the RMS difference between the gauge and the SWOT measurements were about 25 centimeters, and you had many gaps, actually. After we started the validation phase, and I forgot to say, the DEM was not active, okay? So the satellite did not know that there was a station there and where he could prepare the timing for the return, the pulse. So after, during the validation phase, so everything was on, and you can see that the difference between the two series is less than 10 centimeters. So again, just to show that this question of the DEM to prepare your satellite to be ready for the measurement has a great improvement. Now, let's talk about discharge. Everyone measures 8, but one discharge. So the traditional way to, difference from my computers, very sorry. You have you can see the same figure as the one on the Lobai River, the guy having a bath by his gauge. So you can have daily measurements, very often daily readings of the 8. You can perform a few discharge measurements. I insist on this term, a few discharge measurements. No one makes daily measurements, just a few of them. And very sorry. In the middle, you are supposed to have a diagram where you can see that with these two data sets, you have some pairs, and you build a rating curve, and the so-called rating curve. And from this rating curve, every day that you have a measurement of the 8, you can make a prediction of the discharge. Okay? And these are the values you can find on websites such as GRDC. You have no actual measurements on GRDC, except if you look specifically for them. But what you have is daily predictions from your rating curve and your daily readings. And so, and there, you have no information about the quality of the measurements, the true ADCP measurements on the rating curve itself, the relation. What was the spread of the data among the rating curve? And to come back to this question of the quality of the measurements, we also made some experiment about the measurements, ADCP measurements of the discharge in a river. This is on the upper Amazon, and you see a place where the very former measurements need some courage. Okay, not everybody, not at any time could make the measurements. But are just ADCP measurements, much more easy to do, but in two different situations. One was with ADCP joined with some GPS measurement in order that you can track the true trajectory of your ADCP from one reach to the other reach of your river, and the one without, leaving the ADCP work by his own because it is supposed to track by itself to track the trajectory of the equipment. As you can see, the two curves that you have are very different, okay? And it can be almost 50% difference, okay? So the way you have, the equipment you have, the way you make the measurement can make that you have very different results in terms of measurement of discharge. And if we go to Obidos, which is the station on Earth where you have the largest discharge, okay? It's the final station out of the tidal part in the Amazon. So the discharge is about 200,000 cubic meters per second, what you have here. And so you have in blue, in red squares, all the ADCP measurements. Interestingly, you see the red triangles are the old ones. You see that, again, you have a very big difference. For the same value of 8 measure, you had very different discharges. And all the black curves are all the relationships, the rating curves are relationships between the 8 on discharge measurements. And the red one was the official rating curve that we had when we did this, when we plotted this figure, which was in 2014. As you can see, for the very large discharge, rating curve was absolutely off. Sorry. I will talk later on, of course, the blue one on the gray band. But first, you can see that the difference, more or less for you to have an idea, for the value published by ANA, the institution in 2014, the official Brazilian institution, and the last measurement that you have very far after 8 meters was about 1 Congo. Okay, it's 40,000 cubic meters per second, which is more or less 1 Congo, the second river on the world. And then, so more or less, I think that this value published by Collins in Nature paper in 2024, which is that globally speaking, the discharge is at about 20% error. The mean error on the discharge values that you had up to now was about 20%. Actually, from when you want to use space measurements, it's so bad. So bad. Bon, I don't know why. It doesn't. So we do more or less the same way, but with different tools. Okay. The idea is also to have 8 measurements, discharge value, and to make a rating curve in between, a relationship between these two. And so the 8 measurements come from satellite altimetry. Of course, that's what we are talking about. And because we are working in places where we have no discharge measurements, we cannot go there, and we don't want to go there, we will use models. Okay? The models are clearly rain discharge model, for example. And so the point is that with a model, you can have daily estimates, predictions, estimates of the discharge. And so you have infrequent 8 measurements, because the satellites make measurements more or less every 10 or 20 days, not same as gauge readings that can be daily, but you have the daily discharge estimate. So it's more or less the opposite in the time sampling. Okay, but so you can have a prediction for each new altimetry 8 once you have established your rating curve. The big drawback with this technology is that when you talk about rain discharge model, you need rain, okay? And that's really the big point. So rain discharge model, you take the rain, you have a big black box that you tune for your basin, you shake very strongly, and at the output you have some discharge. I don't go into the details. And the problem is, I don't know if I will. No, it doesn't work. Supposed to have a movie on the rain, but the point is that the same as for hydrometry, actually, pluviometry has a big problem in the measurement of the rain in the tropical band. Okay, you have very strong rains in the tropical band, on the Congo basin, on the Amazon basin, in the Southeast Asia, that's not new. But as you can see on the left figure, you have almost no measurement. And this is, of course, one of our big drawbacks.
But just for you to insist on this point, is that this is an example on the Guyana, in French Guyana, where on the left you see the black dots. This is the place where we have rain gauges, okay, on the coast. Very interesting for working on the water flows, just on the coast, at the outlet of the rivers. But we have the advantage that we have the CNES radar, and from the meteor radar, of course, of the Space Center, so we can establish rain maps. And as you can see, the satellite data are, however, much closer to the rain ground truth, I could say, by the radar than given, of course, by the gauges, which are almost useless. And if you want to use these gauges to model the water flow, it's really dramatic. So in that case, we could see that we have this. So although we have this drawback, the point is that we have all the tools for global assessment, and we have a very so now a group, international group with Americans, Germans, French, and I guess English people, and computed globally using this database of 90,000 sites that I showed to you with the Sentinel satellite on cleaning all the series and so on. They could compute rating curve globally for about 27,000 sites. And for this, they used modeling with the VIC model on all the global data set, rain data set, and atmospheric data sets, and so on, that they could use and to publish the rating curves. And so the point is that, again, that this, okay, the advantage of this altimetry series is that they are independent of the political context, of the fights. I will come back later on the budget cuts, and so on. And they provide discharge estimate more or less for free, with a little delay, but more or less for free up to now. Well, let's cross fingers. So to come back to this curve that I already showed you, the blue line is the line that we obtain using satellite altimetry on this, the Brazilian rain discharge model. As you can see, it compares quite well with the in situ rating curves. Okay, we are much closer than all the measurements in yellow, and even for this question of the very last measurement. So, as a conclusion for this question, we can say that the pairs of 8 from altimetry and discharge from the rain discharge model, they are okay. They are less accurate than the 8 or discharge that you can have from in situ measurement. Who knows? But they are much more numerous, and they better sample the extreme flows. Doing this, you can have measurements at very, in particular, extreme flows. As I showed you, in some cases, you cannot go and make the measurement without putting your people in risk, okay? And so the spaceborne rating curves provide, you can say that they provide Q estimates, which are as reliable as the in situ ones, more or less nowadays at more or less 20% of uncertainty. So, given that, the idea for SWOT was to estimate standalone discharge, okay? Not to have to be constrained by the rain quality of the rain or the parameters and so on. So using the very well relationships that discharge is the product between the cross section of your river and the flow velocity, but everyone knows that the velocity is depends most on the friction coefficient, on the slope, on the change in shape of your cross section, and so on. And so actually it's a very non-linear problem, and it's really necessary to assimilate your aids into a non-linear hydrodynamic model with a priori. Because, for example, you have some part of your cross-section that you never access from satellite, which is the part below the lowest value in your series of 8. So, and this has been done, this will probably be the solution used by many people in the future, and it has started from this year with a paper by Kevin Larnier, and what they did is that they combined more or less everything they had, which is that for the age they combined the SWOT measurements, the nadir measurements from the Copernicus satellites, and some of the gauges, very few gauges, but what is very important is that for the model, they use the rain discharge model as a priori solution to have a priori discharge, and they adjusted your model parameters, including the discharge itself, with a hydrodynamic model, which is das flow. Well, all this is more or less a French solution, and they have, I don't go into details, but they are very positive, interesting statistic results. And this will probably be something that everyone will work, the way people will work with in the future. So let's have a look at some societal application. Actually, from the very beginning of satellite altimetry, the people tried to use it for application in the South countries. So among many others, this is an example in Bangladesh, where Hossein, who is an American researcher, but coming from Bangladesh, actually, he used the JSON2 measurements, and including flow modeling from using ECRAS model. So he could build, you see this time series of water level for the very day on prediction. On prediction. I am last, okay? And so they built what they called forecast rating curves. So for each water level they had, they could predict some discharge. Another example is that the flood in Bangui. I don't know if you remember it. It was in 2018. And what we could see in that example is that satellite altimetry was a very good tool because of its synoptic view. Here, for example, so you have the Ubangi city, which was flooded very dramatically. The flood came from the very upstream part of the Ubangi River on the east. But as we can see on all the time series from satellite altimetry, the flood was very visible. And actually, we could so predict the arrival, the coming of this flood a long time ago. What is important is at that time, they were experiencing fights, political fights, and all the data were impossible to get. There is no connection between Bangui city and all the upstream part. So only satellites could bring some information. Okay? And from this information, we computed, for example, at one day, we had a discharge of 11,000 cubic meters with a depth of 10 meters, and you see that the measurements they did in situ are almost the same. So, which again, a proof that it could be used. If people want to use it, it's available, and you can use it. Last example, and bon, of course, it's I wanted just to put it because it's a big cooperation between Lagos, my lab, and CEREGE, which was made on the Lac Chad. And the Lac Chad is an interesting case because, in particular, because it's a place where they experience historical floods, okay, because of the Chari-Logonier water system, but also there is a big, I would say, pharaonic project, Transaqua project, $15 billion, okay, yes, just to divert the Congo waters to Lake Chad, because Lake Chad experienced low water period, and so the governing people, they said, okay, let's go, let's divert the project, okay? The studies made by, in particular, by Florence Sylvestre showed, and colleagues, they showed that the main problem is that the measurements were not so good, okay? The water level measurements were not so good, and actually, what you could see, the water level looks to be rising again, so maybe it's not necessary to divert the water, but the main point is that there is a strong need for proper monitoring of the flood, actually, okay? You see, they wanted to divert the Ubangi River waters, which was flooding. There is no information about this river, and to divert it on the Chad Lake, where they have also very lacking information. So the first point, before they spend $15 billion digging channels and so on, maybe they should measure the rivers. Another big question is so that first they want the point that which is reasoned very often is that they want daily sampling, which today satellites cannot offer. It's a question of the orbital parameters, and they want at low cost. So what can we propose on this? So we, bon, again, it's supposed to be a film, a movie. Bon. So you imagine you have a movie of your satellites with the colleagues from CNRS. We developed, just as you know, on a request from CNRS, we developed a system to show that it was possible to develop a constellation of mini satellites, okay, 10 mini satellites on one orbit. On this, so you could have 20,000 targets hit daily by one of the 10 mini satellites of the constellation. Remember, GRDC is about 10,000 stations. When they have, actually, they receive only 2,500 stations that you can consider that are active, but let's say they have 10,000 because the other are maybe they are just late. Okay. So, bon, very sorry, it was a nice movie from CNRS. And so, what is even more interesting is that what is the cost of such a mission? Okay, 10 satellites and so on. The cost is $1.5 per measurement. If you consider daily measurement, 150 million, it is working for 40,000 stations over 10 years, $1.5 per measurement. If you say, okay, but I don't need all these measurements in North America, in Europe, and so on, I just need 25%, which is about your GRDC measurements, 10,000 stations in GRDC, and the tropical bands, largely speaking, okay? The point is, well, 4 times more, $6 per measurement. Now, how much is it in situ measurement? In situ measurements are about $30 per measurement. Why? Because I took some numbers. Okay, this is rough numbers, okay? But I took number given to me by the Brazilian agency for the monitoring of the Amazon basin, some papers, documents I got for Congo and so on, when they request for money, and the in Guyana where I stayed. So we are far below the in situ cost. And so I finish. And so, as I said, we had a long time of measurement from satellite altimetry. But what's the point nowadays? So we have quite a positive future with the launch of several satellites from the end of this year. We can expect one, and two others. And in particular, we will have the Sentinel-3 NG Topo satellites that should be the follow-on of SWOT. Okay, if we have no budget cuts. Okay, because well, you heard about it. Okay, in Europe they are talking about putting the money elsewhere. Well, again, sorry. What can we conclude about this? Rivers up to 50 meters wide. Daily, we can make it. At competitive cost, we can make it. Discharge estimate discharge at better than 20%. We are almost upon it, but we would appreciate improvement on the other variables such as rain. And for the big point really is the long time series. I'm talking about people working on climate. And with the major point is the connection with the in situ measurements. I showed you that from the 80s, okay, we had a big loss in the in situ measurements, and up to now, we have really a gap to connect the altimetry measurements with the in situ measurements, and this is really the big point. Future may be more positive. Okay, that's it. Thank you very much.
Thank you very much for this nice presentation. Any questions for Stéphane Calmant? Yes?
Thanks a lot, Stéphane, and thank you for bringing us around the world with different basins. My question is, with respect of the very new satellite data we have, how is possible to improve the available hydrological models? And I'm thinking about global models. Because today, if we compare the models we have on the market, they are different. So how we can improve the hydrological models with the new data?
Actually, most of the models, the rain discharge models, okay, most of these models, global models, they give results with similar quality. Okay? The main point is what data they use. For example, for the rain, you have 6 or 7 solutions. The Japanese solution from JAXO, the solution from NASA, and so on. So depending on what you want, where it's good and where it's bad, so you will have different results. But globally, they give reasonably similar results according to the data they use. And the big point to make so the result better would be really to have access to better data, and in particular to better rain measurements from the the constellation of meteor satellites. But it's coming. It's much better now. The result I showed is from the PhD thesis of a student we had in Guyana. And it's coming now if you compare to what we had 10 years ago and so on. It's, well, I would be positive on this. Okay, it's improving. Well, we always want better.
We have another
But because
question?
in particular in this area, again, you have no other measurement. There is no gauge, there is nothing. So the better the results you have, the better the modeling you will do. It's so simple.
Yes, I was wondering from a political point of view, because water discharge data are very sensitive from a political point of view. Do the people to the countries from the south accept, like, yes, to see the discharge data, river discharge data in European database? Because this is what is happening, actually.
Okay.
Well,
No,
I think it's an important question.
Yes, yes. This is this question of acceptability that I talked very briefly at the beginning. It's, you know, well, I don't know if I should say that, but it will come. Okay? The measurement, it's the same as, I don't know, the map, the images that you got from satellites. Okay? The people, they could say, oh, you are spying our country and so on. Okay, it comes. So what we try to do to the governing of, in particular for the basin and so on, is to tell, okay, join us, work with us about it, become experts of the data on your basin and so on. Come with us, because anyway, it will come. And actually, it's not always, the point is not always a question of a political question. It's more a human question about the technicians. We have more problems with the technicians. We are afraid of losing their job more than the politicians, actually.
So how do you explain this decrease in the data? Is it data availability? Is it data measurements? And why is that? Why is this decrease? I would expect something totally different.
So you have addition of situations. Most of these data, they come from the formerly occupied countries, such as in Africa or so on. So after they became independent, okay, they had other problems than collecting the measurements. That's one point. Second point, you see, for example, in Russia or in China, they just don't want to give the data. Okay, to come back to what the other person said, it's just it's a state secret. Okay, they don't want to give the data, and when they give it, I should suggest not to trust it. Okay.
Well, in India, for example, okay, they published some data, and I can tell you that for sure they were very proud to show me how good were the data, which is impossible with the equipment they had. Okay, so, well, and last, in some countries, it's just for US, Europe, and so on. They give it to private companies, okay, that, for example, EDF in France. Okay, the data exists. They are just not given for free access in international database. So if you want the data, 90% of the people using GRDC are researchers or academic people. Okay, so if you want this data, because this is the place where you are supposed to get the data, they just don't want to give it to you. Industrial secret, state secret, and so on. Now, the only one to have globally some data is to go on website. Well, I suggest our website, the HydroWeb, but you have the German one, the Danish one, English one, you have many of the US one, you have many of them if you want. Again, to compare the results, and so, which is a good point. Again, we are talking about physics, okay, measurements. So it's very important to be able to to compare the results. To say, okay, this one looks better, and so on, or this one is rubbish.
Stéphane, so
yes.
I have another question. Thank you for your talk. So the satellite measurement, actually, that you're showing us, that require some, probably some modeling to extract. What is the availability for the southern country?
So, up to now, up to 2016, I would say, early 20s, we tried to train people to extract the very raw information. But now, I think that was not the best way. And because of the technical changes in 2016, now you have much better results just picking the result in the databases, already fully processed, okay? And we should have spent more money in training them how to use this data instead of how to get this data.
Thank you.
So, I'm being told that this is the last question. So, when you investigated the source of misfit between field measurement of water level and satellite data, you showed that some stations had more than 50 centimeters of misfit. So is this purely related to human mistakes, or are there natural phenomena that could explain those misfits?
I will give you just one situation I experienced really myself. I had two series, okay, one upstream, one downstream, a gauge. Okay, my series, with some noise, there is a gauge on my measurements and so on. And at what time, I could see that the difference between my series and the gauge was misplaced. Okay, for example, it was closer to the downstream one, and at what day, boop, it became very close to the upstream one. I talked to the colleagues, the Brazilian colleagues at ANA. I was working over there at that time. I said, there is a problem with the gauge. Oh, Stéphane, your satellites, it's your satellites, and so on. Look at your data, please, don't disturb us. I tell you. Okay, let's go. We went there, okay, and just for joking, the guy said to the local guy who is paid to make the measurements, okay? You see the French guy is spying you from space, and what did you do with your gauge? I did nothing, I swear it. After talking, yes, a boat hit the gauge fall down, but I put it back, okay? And he was just because he has some tools, I would say, he was just 1 meter away. He made a mistake by 1 meter. But because he was a smart guy, this took about 1 week, okay? And because he's paid for the daily measurements, on his small book, he put very smart values of rise of the water day after day. Nobody could see it. Nobody. But you see, he filled up the gap. Just the satellite could see it.
Okay. Thank you.
Just one example. And it's half of the gauges over there. That's life.
Thank you.
Thanks a lot.